Okay, so today basically I will explain to you what is a phi solution, some things about strict sum solution. So now it is working. Okay, so again, we started with a compact metric space, XT, and we have a continuous semi-metric phi defined on X. Phi subsolutions are the functions which are one Lipschitz for phi. And the concatenated cost, I remind you, were defined using the phi cost and the concatenated length. Okay, the phi cost of a chain is just the sum of the consecutive, the phi value between two consecutive points. And the length is the same thing, is the sum of the distance between two consecutive points. So the concatenated cost was defined as the infimum of the cost of a chain joining X to Y of length at least eta. And of course, as we showed, phi 0 is phi. And one important thing is a kind of triangle, improved triangle inequality, or I don't know, semi-group triangle inequality or something like that. How you should call it, but. And once you have the concatenated cost, we introduce the pair barrier as the limit of the soup because phi eta is not decreasing in eta. Okay. And of course, you have phi, the Bayer's barrier is bigger than phi because it's bigger than every phi eta. And it satisfies a mixed triangle inequality with phi, which of course implies a triangular inequality for phi infinity and the fact that phi infinity is either identically plus infinity or it's everywhere finite. The Aubry set was defined as a set of points where phi infinity of xx is 0, can be empty, but it's always closed. And we showed that x is a point in the Aubry set if and only if there exists an eta positive such that phi eta of xx is 0. And this is if and only if this is true for all eta non-negative. Now we showed also that if either x or y is in A phi, then the pair barrier between the 2 points is the same as the phi. And when phi infinity is everywhere finite, we showed that for every xy, to compute the pair barrier between x and y, we have to go somewhere into a point of the Aubry set and then go back from the point of the set to y. By the way, because of this result, this is also phi xc plus phi yc. Okay? And we concluded that the Aubry set is not empty if and only if phi infinity is everywhere finite. It's like recalling whatever is mentioned from the last two lectures. Let me come to phi solution. So a phi solution is first a phi subsolution. Okay, and we are going to ask a little bit more on it. It has to satisfy the following condition for every x. So it's a phi solution at x if there exists a y in x and an eta positive, such that u of x minus u of y is phi eta of yx. Of course, if I don't impose u eta positive, then I can always take x equal y, and then because phi xx is 0, so you have to impose somewhere. So I'm not defining super solution because, I mean, I could define super solution by saying there exists y with large area. But the class of function I obtain does not correspond to viscosity super solution in the case if I come from a Tonelli Lagrange. It's still useful, but I mean, it's not really the one. There are too many of them. So this is, of course, equivalent to equality ux is uy plus phi eta.
But since it's already a subs. Okay, there is equality. It's not, if it's a solution for phi, it's also for phi and subs.
Sorry?
If it's a sub-solution for phi.
And the super solution, in that sense, it's a solution. But super solution is a too big set too. Well, in fact, maybe also for this, because it is solution. You never say anything about the super solution. Yeah, it's. Yeah, you just do the comparison. Well, in fact, you can get the comparison also with the super solution in that case. So of course it's a sub-solution if it's a solution if it's a phi sub-solution which is a phi solution at every x. We'll denote that S phi is a set of phi solutions. Okay. As I said, that's what I said before. Okay. If you are a sub-solution and you satisfy the inequality here, you can get. Okay. Because we are assuming that U is a phi solution. If you have the inequality and U is a phi solution, in fact, this one is less than phi when it's a sub-solution. It's less than phi eta yx for every x. So if you have for one eta the inequality the other way, you just get the equality. Okay. So that's exactly what I say here. In a better form is that you have, so because it's a sub-solution, you have phi eta yx is less than ux minus y for some eta. It satisfies an inequality. Then it's less than phi yx, which is less than phi eta prime x, yx, phi eta x. Okay. So you get that. Now, if we have x in Fi, then every phi subsolution is a solution at x. So subsolution are solution at the reset. Okay, and therefore to check that the phi subsolution is a phi solution, you just have to check it at the point outside of the reset. So because x is in the Aubry set, okay, so I'm going to prove the lemma. Phi eta of xx equals 0 for every eta. Okay, so you get 0 equal ux minus ux equal phi eta xx. Okay, for every eta positive. So it's absolutely, it's a solution itself. Okay. Now, let me recall a fact that I showed is that if you want to compute phi eta of xy, and if x and y are some distance apart, it's just phi of xy till you reach the distance. And after that, it's going to increase. But till eta reaches the distance between the 2 points, it's still phi. Something we showed last time. Now, for every x0 in x, the function is a phi solution at every x different from x0. Therefore, if x0 is in the Aubry set, phi x0 dot is a phi solution because it's automatically a solution at x0, and the one shows you that it's a solution away from x0. And for a given x0 in x, the function phi x0 dot is a phi solution on x, then x0 is in a phi. Okay, so in fact, the Aubry set is the set of point x such that phi x dot is a solution, is a phi solution. For one, fix any x different from x0, since we have phi of x0, x0 equals 0, we have phi of x0, x minus phi of x0, x0 equal phi of x0, x. This tells you, because x is different from x0, you can put here the distance, and it's still phi of x0, x. Okay? Because the distance is not 0, you get that it is the solution of x. Okay? Okay. Now, as I said, 2 follows from 1, because the only point where it could be not a solution in this case with x0, but we show that x0 is automatically a solution. Now, suppose phi of x0, x is a phi solution at x0. Then we can find a y and an eta positive such that phi of x0 minus phi of x0y equal phi eta of y x0. This is expressed that it's a solution at x0. So equivalently, this tells me that phi of x0y plus phi eta y x0 is 0 because this one is 0. Okay? So we get 0 is equal to phi of x0y plus phi of eta y x0. Well, by the triangular inequality you proved, it's larger than phi of eta plus 0 x0 x0, which is phi of x0 x0. Okay, so in fact, phi eta of x0 0 is 0. Okay, but eta is positive, and this implies that, from what we saw, that x0 is in the Aubrey set. Okay, remember we said that x0 was in the Aubrey set if and only if there exists some eta positive, such that phi eta of x0 is 0. So if the Peierls barrier is finite, then for every x in x, the function phi infinity dot is a phi solution. Okay? So, of course, it can be plus infinity than a solution, but well, in some sense, we could say that identically plus infinity is the phi solution that satisfies whatever we want. But I mean, if it's finite valued, it's a phi solution. Phi x dot is a phi solution for every x. So we know it's a phi subsolution. Okay, we must show that phi infinity x dot is a phi solution at y. Okay, for every y in x. So by the property of phi infinity that we gave, we must transit by the Aubrey set to get phi infinity of xy. There is a z in the Aubrey set, such that phi infinity of xc plus phi infinity of xy is phi infinity of xc plus phi infinity of cy. So I can rewrite this as phi infinity of xy minus phi infinity of xc is phi infinity of cy, but this is larger than phi eta of zy for every eta. And as we saw, this implies, of course, that we have the equality because phi infinity of x dot is a subsolution. Okay. So we showed that you want to show it's a subsolution at y, you found the point z such that the difference of value, the function between y, the value of the function at y and z is larger than phi eta of z prime. So we showed this solution.
But it's even equal.
It's equal, of course. But we saw that already at the inequality. This is what I said. Okay. I mean, everything works by itself. You start thinking and just it goes, it rolls by itself. If you find the right concept, then it rolls all by itself.
Ask you a question. So last time you saw that if you take phi to be is U hat, then the preset is everything. So is it also the opposite? So that if the preset is everything, then phi has the special formula, some U hat.
If the preset is everything, yes. Because if the preset is everything, well, okay, I have not shown that the preset, that will come later. You have the representation formula. So basically, that's what we'll give you. Let me, I'm not sure, I have to think of it. But I think it's, yeah, if the preset is everything, then phi infinity of xy is phi. So that, that should do it. Now, we would like to find out when there exists phi solution, and second, to show that phi solutions are stable by uniform convergence. Okay? Okay, if there is no phi solution, we don't really care of that case. But if there are phi solutions, one important property of solutions for viscosity solution was the stability by uniform convergence. So we indeed want this. We showed it for sub-solution, we want it for solution. Now, of course, the uniform convergence is the same as the simple convergence of the family of phi solution, because this family is contained in the family of sub-solution, which is equicontinuous. So the two-point topology will coincide on that set. So this will be the consequence of the following theorem. If I have a phi solution, then for every x in x, we can find a y in x, such that we have u of x minus u of y equal to phi eta yx for all eta non-negative, not just for one positive, but for all eta. Okay. And of course, this is equivalent to ux minus uy is phi infinity of yx. Okay, because if you have this, you have this. But if you have this, this is larger than phi eta of yx for every eta, and we know that because u is a sub-solution, this implies positive. Okay, moreover, we can take y in the Aubry set. We can force the y to be in the Aubry set. So that tells me that if I have a solution, then the Aubry set is not empty. Okay? Now, we'll give a few corollaries and compute some example, and after that, I'll give you the proposition. So the following are equivalent. There exists a phi solution. The Aubry set is not empty. So we showed that that's a direct consequence of the theorem before. And the pairs barrier is finite. That's because 1, 2, and 3 are equivalent, as we showed. The Aubry set is not empty if and only if the pairs barrier is finite. Okay? So 2 is equivalent to 3. 1 implies 2 is the theorem showed above. And 3 implies 1, since we showed that when phi infinity is finite, then phi x dot is a phi solution for every x in x. So the phi solution, second corollary, the phi solutions are stable by uniform convergence. So suppose you have a sequence UN of phi solutions that converge uniformly on X to a function U from X into R, fix X in X. So we want to show that the uniform limit U of the solution U1 is itself a phi solution at X. By the theorem above applied to UN, for each n, we can find a yn such that UNX minus UNYN is phi infinity of YNX. Okay. Extracting, if necessary, we can suppose that Yn converges to Y, we are in a compact space. And therefore, the convergence of UN to U is uniform. So the left-hand side is going to converge to UX minus Y. And this one is continuous. So this is going to converge to phi YX. Okay? And now, the next corollary is just the representation formula, which is well known for Tonelli-Lagrangian, is that if U is a phi solution, then it is equal to the infimum for Y in U phi of Uy plus phi of Yx. So in particular, two solutions which coincide on the Aubry set coincide everywhere. Okay. So if U is just a phi subsolution, I have the inequality. Ux is less than Uy plus phi Yx. So certainly, if it's a subsolution, I have the inequality. Ux is less than the infimum of Uy plus phi Yx, with Y in Fi, in the Aubry set. Now, to show the equality, it remains to show the converse inequality. Now, from the theorem above, we can find a y0 in the Aubry set, such that Ux is Uy0 plus phi infinity of y0x, but phi infinity is larger than phi of y0x. And this quantity here, because y0 is in the Aubry set, is larger than the limit. Okay. Now, let me compute the example. Let me speak about the example. So XD is a compact metric space. So we start with the U-hat case. So we showed that the Aubry set is everything. Since any U subsolution is a U solution at every point, okay, we obtain that SU is equal to the subsolution, okay. And this, as we saw before in this example, the subsolution are just U plus constant. Now, if we take phi d equal d, then the Aubry set is empty. The Aubry set is empty, and therefore there is no solution. Now, the last example is again, we take the semi-metric is d, but the distance is d to the power alpha for some alpha positive. If x has no isolated point, we showed that if phi is the whole of x, okay, therefore, well, this is the so this is a counter example to the question. Okay. So this is a counter example to the question. We take a semi-metric phi equals d and distance d to the power alpha if x has no isolated point. We show that Fi is the whole of x. Okay. In that case, we have because Fi is the whole of x, while every subsolution is a solution at every point of x. So the solutions are the same as the subsolution, but the subsolution are the function which are Lipschitz for d with Lipschitz constant less than 1. Okay. and this is not difference of the function. Does not generate.
Yeah, the problem is that there is more than one solution, right?
Yes. No, but the point here, you see that for Lagrangian, you have something. It's that phi vanishes to second order. Okay? Subsolution vanishes to second order on the rubric set. And this is not the case for a general phi. Okay, and the reason comes from the strict convexity and the superlinearity. Okay.
Yeah, but if the preset is everything and the solution modif are just translation by constant, then it's true that phi.
Exactly. Yeah. Because the phi x dot are solutions. So the difference between of them is a solution. That's it. Okay. Now I have to give the proof of the theorem. If I have a phi solution, then I can find a y such that ux minus uy is phi eta yx for all eta non-negative. Okay, and moreover, I can take it in the Aubry set. And this is equivalent to ux minus uy is phi infinity of yx. Okay, so suppose you have a phi solution everywhere on x. Fix x, and you define Ix as the set of non-negative eta for which there exists a y such that ux minus uy is phi eta of yx. Okay? This is in fact an interval starting at 0, because we saw that, okay, we saw that if uy minus ux, I'm going to write it here, is larger than phi eta yx, okay, and use absolute. A kind of miracle happened.
Yes.
I can write. It happened. This morning I wake up and I improved infinitely.
Yeah, bro.
Hmm? Yeah, no, it's not wrong. It's the usual thing, you know. After the surgery I had, my physiotherapist told me by mid-December you will have recovered all movements of your.
Good.
So, well, then I have to improve musculation. So it's not finished. So this implies that, in fact, u of y minus u of x is phi of eta prime yx for all eta prime less than eta. So it's an interval. It's not really important here, but we will use it again to present it. Okay, so it contains 0 and a positive number because it's a subsolution. Now, I'm going to take the soup of this value. I call it eta x. Okay? Eta x is positive because there is a positive number there. And so we can find a non-decreasing sequence or a strictly increasing sequence such that eta n converges to eta x. Okay? So eta n is strictly less than eta x. And the eta n are in Ix. Okay. So by definition of Ix, because the eta n are in Ix, for every n, I can find yn, okay, such that ux minus u of yn is phi eta n of yx. This is the definition of eta n being in Ix. Okay, but in fact, if I look at ux minus ym, this is phi of eta m, phi of ymx, but because eta n is increasing, okay, this is true for all n. You have inequality here for all n less than m. Okay? Now, by compactness, I can suppose that yn goes to y. Okay? And by continuity of u and u of phi eta, okay? Now, n is fixed. Continuity of u, and this one, the inequality here, I let m go to infinity. I let m go to infinity. This inequality now, I know what it tends to. I get ux minus uy is larger than phi eta n yx for every n. Okay? I fix n, and I let m go to infinity, I get that. Okay. So in fact, I have equality, but I'll use it later. But now, I'm not saying that u is just a solution at x, because I couldn't prove what I say. Okay? But I am assuming that u is a solution everywhere. So it's a solution at y, at the y that I found here. Which means that I can find eta bar positive and y bar such that u of y minus u of y bar is equal to phi eta bar y bar y, because it's a solution there. So what I do, we add this inequality, this equality in fact, to the inequality that we have established for every n. And so we get that ux minus u of y bar now, okay, is larger than phi of eta bar y bar y plus phi eta n yx. Okay? But now we know that phi eta bar y bar y plus phi eta n yx is larger than phi eta n eta bar y bar x. So we get this inequality for every n. Okay? But the inequality implies the equality. That's what we said here. But this means then that eta n plus eta bar is in Ix. Okay? This is the definition of Ix. And therefore, eta n plus eta bar is less than eta x. Okay? But now I can let n tend to infinity. This goes to eta x plus eta bar less than eta x, but eta bar was positive. So this implies, in fact, that eta x is plus infinity. Okay? So this forces eta x to be plus infinity. Now, I have established these inequalities, okay, with the y, which is independent of n. I can let now eta n go to infinity, okay? Or I can just say that because eta n goes to infinity and phi eta is non-decreasing, I have the inequality for every eta, okay? And because it's a phi solution, I have equality everywhere for every eta, and therefore okay, I get this one. Now I still have to show that I can choose y in the Aubry set. A priori, y is not in the Aubry set. Okay. Now, the equality ux minus uy equal phi infinity of yx implies that phi infinity is finite. Because phi infinity is finite, to compute phi infinity between y and x, I must transit from another point in the Aubry set. Okay? So I can find the z in the Aubry set such that phi infinity of yx is phi infinity yz plus phi infinity of zx. Therefore, ux minus uy So I use ux minus uy is phi infinity of yx. And so I get ux minus uy, okay, I replace this by phi infinity yz plus phi infinity zx. Okay? But u is a subsolution, so uc minus uy is less than phi of yz, less than phi of the infinity of yz, and ux minus uz is less than phi zx, which is less than phi infinity, okay, of zx. So if I add these two, I get ux minus uy is less than phi yz plus phi zx, which is less than phi infinity of yz plus phi infinity of zx. Okay? But this is an equality because ux minus uy is the sum of phi infinity yz plus phi infinity of zx. So you are adding two inequalities and get an equality. Each inequality must be an equality. Okay? So this forces the inequalities above to be equalities. In particular, you get no, I get, it's not this one. It's ux minus uz equal phi of zx. It's the first one, the second one. Okay, so you get, this is an equality, so you get ux minus uz equal phi infinity. Okay, and z now is in the opposite. Okay. So I showed that to know that there is phi solution, you have to know that the pair of pair is finite, or the reset is not empty. I also showed the closure by uniform convergence of phi solution, and I showed that phi solution are completely given by their value on the home reset, like the usual case. Now, I'm going to speak of strict subsolution. Okay. One reason I speak of strict subsolution is that they imply the comparison principle existence. Implies the comparison. Okay. And they are useful anyway. So in that case, we have the mother relation and strict subsolution. So what is the mother relation on x times x? X is mother related to y if and only if the symmetrize of y of phi between x and y is 0. So phi y plus phi x is 0. The graph of this relation is denoted by graph mother of phi. Okay. It's a set of pairs xy such that phi xy plus phi yx equals 0. The mother relation is an equivalence relation, and the graph is contained in the product of the reset by union the diagonal. Of course, the diagonal is always included in the graph in an equivalence relation. So, and therefore, it means that if we have 2 points which are mother equivalent, they are both contained, 2 different points, 2 distinct points. They will be both contained in the home reset, but they cannot be contained in the name. They are distinct. The pair is not in the diagonal. Okay. So when the Aubry set is empty, the mother relation is the identity relation. So the mother relation is symmetric, satisfies from the triangle inequality. It's transitive. Okay, I'm not going to. It's simple fact. And of course, it's symmetric. Now, suppose that you have 2 points which satisfy phi of yx. Okay, so we want to show that whatever is not in the diagonal is included in the product of the Aubry set by itself. So we take a pair of points which are distinct and which are in the graph. So they satisfy phi x plus phi yx is 0. Okay. So phi of xy is phi of the distance from xy by the distance xy xy and also the other one. So we get that 0, which is because of the equalities, and the sum is 0. So we get that 0 plus phi txy xy plus phi txy yx, which is larger than phi of x, but for 2 txy, this is larger than phi x is 0. So we get that this one is 0, but distance from x to y is positive, so x is 0. Okay. And same thing for y. So a subsolution satisfies that. So we want to know, to understand when for a given pair xy, the inequality above is always an equality whatever subsolution you use. Okay. And here is the first answer. Suppose U is a phi subsolution and the pair xy is in the graph of the mother relation, then necessarily uy minus ux is phi of xy. So here is your answer to your question. Okay. If the graph, if all points are mother equivalent, then you have a unique solution, then you get what you want. And the point, as I said, is that the fact that subsolution is degenerate up to second order, it's identity. The derivative is 0 and the second order term is 0. In the case of Tonelli-Lagrangian, tells you that you have one class. So in other words, we have that the graph of mother is included in the set of pairs xy such that uy minus ux is equal to phi of xy. And this is for every subsolution. So the next question will be, can we find such a U with equality? That's what we will do. And this is what is called the strict subsolution. Okay, so why is it like that? For every pair xy of points in X, we have uy minus ux is less than phi of xy, and ux minus uy is less than phi of yx. So we get 0 is ux minus uy plus uy minus ux is less than phi of xy plus phi of yx. Okay? When xy is in the graph, the mother relation, then this is 0. So the sum of the two inequalities is 0. So both of them are equal. Two inequalities here must be equality because the sum is an equality. Okay? And that proves the first proposition. So this suggests the following definition: a phi solution U is said to be strict if the graph of the mother relation is exactly the set of points xy such that u of y minus ux equal 5x. Okay. There exists a strict phi subsolution. Pick a sequence Ci dense in X and find a sequence eta I positive whose sum is 1. Positive number whose sum is 1. So you look at the convex combination of subsolution, because subsolution are closed by finite convex combination and under uniform convergence. Okay. This is a subsolution. Okay. And therefore, we know that the graph, the mother graph, is contained in the set of points xy such not equal, such that not included, but such that theta y minus theta x is phi of xy. Since this inclusion is true for all phi subscripts. So we have to prove the converse. Okay, so suppose that phi theta y minus theta x is phi of xy. Now, because phi ci dot is a subsolution, I have the inequality without the ai, eta I, so I can multiply by the eta I, which are negative, have the equality. Then I sum, okay? And so I get here the difference of values of theta between y and x is less than phi of xy, but I am assuming that it's phi of xy, so I have equality here. Okay. Again, this implies equality in every one of the equations above, but ai is not 0, eta I is not 0. Okay. All the inequalities are equalities. And because eta I is not 0, we conclude that phi of zi y minus phi of zi x is phi of xy. Okay, so if we know that theta y minus theta x is phi of xy, we know that this is true for every I. But we choose the zi dense. So this tells me that phi of zy minus phi of zx is phi of xy for all z in x, because phi is continuous. So in particular, if I put y here for z, okay, so we just showed that. Taking z equal y, I get minus phi yx is equal to phi of xy. So equivalently, this tells me that phi of yx plus phi of xy plus phi of yx is 0, which means that we are in the mother. So in particular, if the Aubry set is empty, then there exists a phi subsolution such that theta y minus theta x is strictly less than phi xy for all xy with x. Okay. Because this tells us that the graph of the mother set, the graph of the mother relation is just the diagonal, and therefore the proposition above must satisfy theta y minus theta x is different from phi xy when x is different. Okay. And that's it for today. And once you have strict subsolution, then you can show a comparison principle. Okay. comparison principle, I mean, people always use the fact that you have something which is strict somewhere to get equality. If not, you cannot do it.
Yes, what do you mean by?
Well, I mean, when you compare sub-solution, viscosity sub-solution and super-solution, you want to make the sub-solution at least in the neighborhood of a point, a sub-solution of something with a smaller constant, Hamiltonian constant. This is the way you prevent the maximum from being on the boundary. Okay, so I don't know when will be next lecture. I forgot.
Monday, next.
This Monday?
December 2nd.
Okay.
Okay, any question? So let us.
Yes.
Yeah.
Yes, I'm wondering because here you define the areas barrier and also the phi eta, and then you never use, you showed some properties on them, and then you only use this property. You never use what they are. So is there, I don't know, characterization of this function? Like if you have this property, can you recover the definition? Because
Phi?
Yes, of phi eta, the barrier value. It seems a bit universal, everything that you deduce.
It is universal, but the problem, okay, for example, when phi infinity is plus infinity, I'm dead, yes.
Okay, yes.
Okay.
And another question, you mentioned briefly that here you assume compactness of X, but because it's simpler, but you would say.
Well, you have you have to do modification. Okay, the statement as I put them are not correct. You have to do some modification, but you can do it for non-compact. Okay. You have to put some hypothesis and make sure that. Okay.
Other questions? Let us back up there again.